thinking about that sun, earth, moon alignment, let's talk about the really exciting solar eclipses. So solar eclipses happen only at new moon. You have to have the sun, moon, earth alignment. Now, this top picture is way off scale. Here's it a little bit properly scaled here of the sun way off your screen, several meters to the left here, and your moon casting a shadow onto the earth. And you'll notice that there is a darker region and a slightly illuminated region, and we'll properly define this shortly. But before we get to all that, let's think about this a little bit. What is the primary reason that the moon can block out the sun and create those total solar eclipses that we see on Earth, those beautiful pictures of the moon blocking out the sun? Is it just the fact of the distances between the Earth, sun, and moon? What about the diameter? Is it the ratio of the diameter of the sun to the surface area of the moon? Or is it this angular size of the sun to the angular size of the moon? Or is it something about those gravitational pulls? We've got the sun pulling on the moon, moon pulling on Earth, sun pulling on Earth. Is it something about that interaction? So pause the video, give yourself a moment to think of your answer, and come back. All right? So what I would say is that it's the angular size that is the primary cause. Yes, the distances matter. The diameter of the sun will have a factor in there, but if I wanted to say one term that describes it, it's that angular size quantity. So a reminder, the angular size, that says how big does an object appear. It's dependent on how far away that object is versus how big the object is. So here are the values. If we look at the diameter of the moon, it's 3 times 10 to the 6 meters diameter, and it is 4 times 10 to the 8 meters away from us. Whereas the sun's diameter, how big the sun is 1.4 times 10 to the 9th meters. While the distance to the sun, remember that astronomical unit, is 1.5 times 10 to the 11th meters. So let's calculate the angular size of this moon and the sun from here on Earth. The moon's angular size is 0.0086 radians. Converting that into degrees, I know most of us are a bit more comfortable with that. You'll find that the moon's angular size is 0.49 degrees. The sun comes out to 0.0094 radians, or 0.54 degrees. And that's the remarkable quantity. Even though the sun and the moon are drastically different sizes and drastically different distances across the solar system away from us, their angular size is approximately the same. They're both approximately 0.5 degrees. And it's that special property between the sun, earth, moon relationship that allows beautiful solar eclipses to happen. There are 3 types of solar eclipses. On the bottom here, we're seeing a picture of a total eclipse before and after it happens. So here's the sun and the moon is coming in, blocking, moving in. There's your total solar eclipse. This section here is what we call the corona of the sun. These are the upper layer atmospheres, the highest, most energetic. This is the hottest region of the sun, actually. And we only get to see it during these total solar eclipses. But they're very brief, only a minute, sometimes very short. And the moon will continue on, right? So this is an example of a total solar eclipse. There also could be partial or annular eclipses. So let's look back at a previous figure here and see where on the Earth you are to get different types of eclipses. So here's that dark region. You happen to be living here in the dark region, or have traveled, you'll get to see that total solar eclipse. But if you're outside, you'll be regions where you'll get the partial eclipses. You're outside that region where you get to see the moon perfectly line up with the sun. So, speaking of traveling to get that nice perfect shot, the last solar eclipse across the continental United States happened on August 21st, 2017, and I went on a road trip with several of my friends. And this was us after we climbed up a mountainside. We had to park about a mile and a half away. Hundreds of people. There were people scattered all over the mountainside. And this was just normal afternoon. Big park, beautiful day. And this is still the middle of the afternoon. It's a very fascinating thing as the eclipse comes in. It starts to look like sunset, but the sun isn't anywhere near the horizon. Now, on this day, we were terrified that we weren't going to be able to see the total eclipse, but we actually got a very interesting effect here. Normally, you can't look at the eclipse with a blind naked eye. You need those special solar glasses. But the cloud cover came in for us. We were terrified we were going to miss it, but in fact, we were able to witness the solar eclipse straight through the clouds. I was able to take this with my cell phone. It was a lot of fun. Coming back, let's define these regions of the shadows now. Oh, if you could be in the umbra, the total part, this is where you'll find the total eclipse at this cross section here. It's produced by light from the sun being completely blocked off. If you're behind this point though, if Earth's position, Earth has to be here, you have to be right there to get that total eclipse. But let's say the Earth's alignment was slightly off and the Earth position was just a little bit back here. Then you'd be in an annular eclipse. Right? Total eclipse, boom, you get to see that corona. And an annular eclipse, the moon, the angular sizes don't quite line up. You don't quite get to see the sun completely blocked off. You get this ring shape around there. Now, if you're in the moon's penumbra, part of the light is being blocked by the moon, but there's a shadow being cast. This light is being illuminated by the light of the sun up here, but it's also not as bright because of the moon blocking some of the light. So you can be in these penumbras, and you'll get partial eclipses. Flipping things around a bit now, let's get away from solar eclipses and talk about the lunar eclipses. So here the setup will be the sun, earth, and moon. And the moon will be in the umbra of Earth's shadow, and there's the penumbras of Earth's shadow. Now, once again, looking at this to scale, it goes Earth, much bigger shadow across the moon. So lunar eclipses only occur at full moon. Remember, it has to be sun, earth, moon. And this will happen more frequently. It's visible over a wider area. So what is the frequency of these eclipses? So to be specific, you only can have either a solar eclipse or a lunar eclipse when the sun, earth, and moon are lined up in a nice straight line. But the moon's orbit around Earth is tilted by about 5 degrees, 5.2 degrees. So the moon will intersect this plane here, this yellow plane here, dip below it, intersect again. So it's at the points of these intersections when the moon is crossing through. These are the only times that we'll see eclipses here. And that's the reason why we don't get to see eclipses every month. It has to be, you have to wait for this alignment of the orbit to come together correctly. So as a summary, let's wrap up section 2 now. We talked about this celestial sphere, and that is this imaginary sphere that we're projecting the stars and planets onto. Right? And the celestial sphere is what we from Earth see the universe as. We talked about the angular size. It says how big an object appears is related to how big it is divided by how far away it is from us. And we established that the Earth is rotating in that ecliptic plane. Our rotation axis around the sun is tilted by 23.5 degrees, and that 23.5 degree tilt is the reason for the seasons. Then we talked about the positions of the sun, earth, and moon, and how we can create the lunar phases and solar eclipses versus lunar eclipses. All right, that's the end of section 2.